is SCH4U, enthalpy, and enthalpy change. The Ontario curriculum would like for us to be able to talk about chemical processes based on energy changes and to investigate various physical chemical processes and the energies associated with them. So, when we want to talk about energy of reactions, the first thing we need to do is to define this funny term enthalpy. And enthalpy is a source of some confusion. It really need not be. All it is the energy in a system in total, the thermal energy of a system. And what's interesting about it is we'll most often talk about the change in that energy. And the reason why is because it's very hard to measure the total energy in that system. It's much easier to talk about the change from one state to another. And so we'll focus most of our energy, bit of a pun, on the idea of enthalpy change. So the enthalpy change is the energy change in a physical or chemical reaction. Now we've talked briefly about the idea of systems. This enthalpy change of a chemical system will be equal to the flow of thermal energy into or out of the system. And this is why calorimetry and other techniques of measuring the flow of energy into and out of the system are so important, because those give us an idea of the enthalpy change. Now, of course, the first law of thermodynamics, law of conservation of energy, underlies this entire unit. And really, that first law is just a restatement of what we see right here. The change in energy of the surroundings is equal to the change in energy of our system, except opposite in sign. I think you can see that. If our system goes up in energy, that energy had to come from somewhere. It comes from the surrounding universe. In contrast, if the energy level of the surrounding universe goes up, well, that energy had to come from somewhere. It came from our system. And so this is maybe the easiest equation we're ever going to cover in science. Now, a little bit of a definition then. If the energy of our surroundings goes down, in other words, if the change is less than zero, then that energy is being taken from the universe and put into our system in order to activate our reaction. So what we say is that's an endothermic reaction. It's using the energy from the universe in order to make that reaction occur. And of course, we can have the opposite situation where energy is being transferred from our system to the surroundings, and we call that an exothermic reaction. So it's probably a good idea to illustrate these with some examples we can handle. We will quantify the change in energy of our system, the change in enthalpy of our system, based on this simple idea of the change in energy of our system is equal to the energy of our products minus the energy of our reactants. So the final energy level subtracting the initial energy level. And this delta H then, this changed enthalpy, is the heat given off. Now, we have an important definition to cover, or an important constraint to cover, that will become more obvious later. So when we're talking about delta H, we need to remember that it's at constant pressure. If there's a pressure change, then there's more going on and the system gets more complicated. So let's look at two chemical processes then in order to illustrate our situation. So we're going to look at this situation. Now pay attention to the direction of the arrow. So our initial state is 2 molecules or 2 moles of hydrogen in gas form and 1 mole of oxygen in gas form. And these are reacted to form 2 moles of liquid water. Now, most of you will recognize that this is an oxidation reaction. In fact, it's combustion. So we're burning the hydrogen in the presence of oxygen. The energy of the system initially is very high. There's a lot of chemical energy held inside these bonds. The reaction occurs and it gives off heat to the surroundings. Of course, we're burning the hydrogen, so this isn't hard to imagine. And then when we're finished, there is less energy contained within these bonds. Our system's at a lower energy level. That energy, of course, is the heat that's given off to the surroundings. This is an exothermic reaction. Now, in contrast, the reaction on the right, we're taking mercury oxide, 2 moles of it, and it decomposes to liquid mercury and oxygen gas. Now, this one we're not so familiar with, but what we can say is the only way to make mercury oxide in solid form convert to liquid mercury is by putting in heat. We have to heat it up. This is an endothermic reaction. Heat from the surroundings goes into converting mercury oxide to liquid mercury. So this is an endothermic reaction. The energy level of our products is higher than our energy level of our reactants. Where does this energy come from? It comes from the surroundings. So in one case, the energy of the products is less than the energy of the reactants. That energy goes off into the universe. In the other case, and delta H is less than 0. In the other case, the energy level of the products is greater than the energy level of the reactants, and delta H is greater than 0. Now, we can also talk about enthalpy change, not just in terms of a system in which, for example, we have 5 grams of mercury oxide. We can also have enthalpy change associated with a mole of a substance. And this can be a very useful construct when it comes time to, for example, scale up a reaction where we have to calculate how much energy will be produced and see if we have a sufficient cooling system to prevent an explosion. Now, so molar enthalpies then are associated with a given balanced reaction. So we can have a molar enthalpy of solution in which sodium bromide dissolves to form aqueous sodium and aqueous bromine. Notice, of course, that there would be charges on there if we've been a little more careful about our reaction. We can have the molar enthalpy of combustion, in this case methane, burning in the presence of oxygen to form carbon dioxide and liquid water. Molar enthalpy of vaporization, all we're doing is taking, in this case, liquid methanol and converting it to gas form. And you get the idea. Freezing, but here's an interesting one, neutralization. So in this case, we have aqueous sodium hydroxide reacting with sulfuric acid to form an aqueous salt and liquid water. This can also have a heated reaction associated with it, a molar enthalpy change. And some of you may have noted that when you add an acid and a base together, a lot of heat can be generated. Well, this is this molar enthalpy of neutralization. We will talk more about enthalpy of formation later, but this is by definition converting elemental components to some compound. Now, if we want to look at the enthalpy of a given system, like we talked about at the beginning, to see if a lot of heat will be generated that we need to deal with in a chemical process, we would take our molar enthalpy and calculate the enthalpy of the system by calculating the number of moles involved. So these molar enthalpies, or heats of reaction, have been tabulated for us in many cases, and we can look these up online for certain systems. We can look at our tables that are provided to us. These are here for reference. So we've got a heat of neutralization. We can expect to notice the negative sign. So this is an exothermic reaction. We can expect to get 56.2 kilojoules for every mole of hydrochloric acid we neutralize with sodium hydroxide. Heat of fusion, this is an interesting one. So in order to melt a mole of water, we need 6 kilojoules, 6.01 kilojoules. Notice that it's considerably more. Boiling requires considerably more energy. In terms of doing calculations then, we can look at this type of question, and there are lots of them. There are thousands and thousands of examples, and we'll get to them in the worksheet for today. So this is an example. Some of you may have noted that when isopropyl or another alcohol is used to disinfect your skin, it feels cold. Well, here's a calculation associated with this. Let's imagine that a doctor is disinfecting your skin prior to giving you an injection. And so she uses 1 gram of ethanol, spreading it across your skin, and that ethanol evaporates. What's the enthalpy change? Well, first off, we need the molar enthalpy of vaporization of ethanol. It's 38.6 kilojoules per mole. Notice that the sign is positive. So then we can collect our givens. Our mass of ethanol is 1 gram. We have our heat of vaporization is 38.6 kilojoules per mole. And then we need to get out the periodic table and figure out the molar mass of ethanol. Which is 46 grams per mole. Given this, we can calculate the number of moles of ethanol. So that's 1 gram over 46, call it 0.022 moles of ethanol. And then what we can do is simply multiply out. So our overall change in energy will be the number of moles times the heat of vaporization. And we get about 0.836 kilojoules. Notice it's no longer per mole. We've multiplied moles times kilojoules per mole to get kilojoules. So what does that mean in real terms? It means your skin isn't just feeling cool. Your body is providing 0.836 kilojoules to the process of vaporization of ethanol. Now, when we want to report these kinds of energy changes, there are some challenges associated with the signs. Of course, we've already alluded to this. We need to be very careful with the signs. There are several, though, ways that are acceptable for communicating these energy changes in thermochemical equations. Of course, we've already discussed endothermic enthalpy changes are positive values. So in this case, we have the decomposition of water to hydrogen and oxygen. And so this requires energy. This is the opposite of burning. It requires energy. So we have our delta H beside the equation. Exothermic will be negative. So if we reverse this equation, of course, the first law suggests that the same amount of energy is going to be involved, but the sign changes. We get out 285.8 kilojoules per mole of hydrogen. Now we can communicate these energy changes in the way shown above, but there are 4 acceptable ways that you can communicate these on a test. One of them is a diagram, the other 3 are thermochemical equations. So this way we haven't really talked about before, but this is a perfectly acceptable way to communicate the energy change in a reaction. What we can do is we can include energy as a product or as a reactant, depending on whether it's exothermic or endothermic. So let me put this into words and it should be fairly obvious. We react methanol with oxygen to form carbon dioxide and water, plus we evolve or we generate 726 kilojoules. Now notice we didn't quite say per mole here. Well, there's a good reason for this. Per mole of what? So in this case, we could, if we wanted to, multiply all of these terms by 2 and get 2 methanol plus 3 oxygen to 2 carbon dioxide plus 4 water. Well, if we did that, we would have to multiply this energy by 2 as well. So we don't say by mole. We say the equation as written will generate 726 kilojoules. Okay, so let's look at a different way to do it. This is the way we've done so much so far. This is the same equation, but instead of writing the energy as one of the terms in the equation, we write beside it a sort of a second term or a second equation beside it, saying that the change in energy of the reaction as written will be negative 726 kilojoules. And it's still an exothermic reaction. The sign has changed because we've changed it to a delta H communication. Now, we can also, instead of doing this, write the molar enthalpy of a specific reaction. So in this case, notice that we changed this to kilojoules per mole. When we do this, we have to specify per mole of what? Because the answer is not negative 726 kilojoules per mole of oxygen, because we use a different amount of oxygen. So this is typically done by choosing the reactant. So we could say that the molar enthalpy of combustion of methanol is negative 726 kilojoules per mole of methanol. Hopefully that's clear. The key is to avoid being confusing, being ambiguous about which molecule is the molecule of reference. Now the other thing we can do to communicate this is give a potential energy diagram. And we'll do that in the next couple of slides, and we've already hinted at that previously in any case. But one note about fractions. They can be very convenient in thermochemical equations. We've got a fraction 3/2 up above. They can be convenient. Now, one thing we do need to keep in mind, we can't have fractions of molecules. The 3/2 up here refers to 1.5 moles of oxygen, not 1.5 molecules. Okay, our potential energy diagram then. This is a different equation but the same kind of idea. Notice the direction of the arrow. Solid water, ice, is being converted into liquid water. So, when we do this, the enthalpy change will be 6.01 kilojoules. The system's absorbing heat, it's endothermic. And here, it is implied that's per mole of water. And another way of saying it then, 6.01 kilojoules are absorbed for every mole of ice that melts at 0 degrees Celsius in 1 atmosphere. And this is roughly the same thing as saying this. So, another example, here is the conversion of methanol in gas form, the reaction of it with oxygen in gas form to form gaseous CO2 and liquid water. This is combustion. So, notice the direction of the arrow. We're converting methane to carbon dioxide. The heat of combustion is negative 890.4 kilojoules per mole. Delta H is negative, which means the system gives off heat to the surroundings, and it's exothermic. And another way of stating this then, 890.4 kilojoules are released for every mole of methane that's combusted at 25 degrees C and 1 atmosphere. So, to summarize, enthalpy is the heat change associated with a process. Exothermic reactions have a negative enthalpy of reaction. Endothermic reactions have a positive enthalpy of reaction. For your homework then, please read over the note and go ahead and work on the 2 worksheets. Don't forget that for today, there are 2 separate presentations. Thank you very much, and have a wonderful night.